This video is part of my complete practical CCNA course, where I use physical devices to explain and demonstrate topics in the CCNA exam. I think it's really important that you see how things actually work, real routers and switches, real computers, rather than just learning about this from a theoretical point of view or in a simulated environment. You actually see how things work. In this video, I'm going to show you how a network can be destroyed or melted if spanning tree is not configured properly and a loop is formed, because we're going to cover two topics in this video: BPDU filtering and loop guard. Spanning tree was created to stop loops in a layer 2 switched environment, and this is what can happen if you introduce a loop into a topology. Simple network like this is going to be destroyed because spanning tree is not working as it should. Let's first cover BPDU filtering, and then we'll talk about BPDU guard. I'll show you in a demonstration how BPDU filtering can destroy this little network, and then I'll show you how you can use BPDU guard to solve the problem and basically stop a network meltdown. Now, it's very seldom that you want to disable spanning tree or stop BPDUs being sent or received in a network. So it's very seldom that you're going to do this. But in this example, we've got a service provider network on the left-hand side, a customer network on the right-hand side. The service provider is not going to want BPDUs from the customer affecting their spanning tree. So basically, we want two separate spanning trees here. We don't want this spanning tree on the right affecting the spanning tree on the left. So in other words, on this port in the service provider network, we may enable BPDU filtering so that we ignore BPDUs sent by the customer as an example, and we don't send BPDUs to the customer. It's important in this topology that there be no redundant links, layer 2 links between the service provider and the customer. This is again why today we often prefer layer 3 links rather than layer 2 links using spanning tree. We'd rather have routed links in a lot of topologies because then we don't have to deal with the kind of nonsense that I'm going to show you in a moment. Okay, so how does BPDU filtering work? It doesn't block an interface like BPDU guard does. It instead filters or blocks the BPDUs. Very important, there is a difference between interface and global configuration options. Be very careful enabling BPDU guard on an interface, as I'm going to demonstrate in a moment. Okay, so make sure you understand the following difference. When applied globally, it affects all port-fast ports that don't have BPDU filtering configured on them. Notice this affects port-fast ports. If a BPDU is received, port-fast is removed from the port, BPDU filtering is disabled, and spanning tree sends and receives BPDUs. In other words, it basically becomes a normal spanning tree port. Sends BPDUs, receives BPDUs, port-fast is removed, BPDU filtering is removed. Upon startup, the port transmits 10 BPDUs by default. If any BPDUs are received during that time, port-fast and BPDU filtering are disabled. Again, this applies when you enable BPDU filtering globally on the switch. The whole idea is port-fast ports that don't have BPDU filtering enabled on them specifically have this setting set. If a BPDU is received, port-fast is removed, BPDU filtering is disabled, and basically acts like a standard spanning tree port. Now, this is the cautionary tale one. If you enable BPDU filtering on an interface, BPDUs that are received are ignored and no BPDUs are sent. In other words, it's kind of like disabling spanning tree. Very bad idea. As I've mentioned a few times now, be very careful using this because it can cause a loop. And of course, we're going to demonstrate that. This is how you enable it globally. Conf-T, spanning tree, port-fast, BPDU filter, default. Notice this is affecting a spanning tree port-fast port. So we've got port-fast enabled on gigabit 102. You enable the port-fast command on the interface, but then you type exit to go back to global configuration mode, and you enable this port-fast BPDU filtering command globally on the switch. Show spanning tree summary shows us that port-fast BPDU filtering default is enabled. This is how you enable it on an individual interface. So I've done it on a range of interfaces here. These ports are set as port-fast ports. So gigabit 102 to 3, I've enabled port-fast and I've enabled BPDU filtering on those two ports. So you could do that on an individual interface or a range of interfaces, but notice this command is typed on an interface or range of interfaces. It's not configured globally. Now, rather than showing you a demonstration of that by itself, I'm going to talk about loop guard first, and then I'm going to demonstrate filtering and loop guard together so that you can see the problem where the network breaks, and then I'll show you how loop guard can solve the problem by stopping the loop. Okay, so let's discuss loop guard. In this example, I've got a fiber cable and I'm shining visible light through the transmit and receive parts of the cable. That's a potential issue in fiber cables because one side is transmit, one side is receive. If there's a problem with one of the cables, so as an example, I'll turn off the light here, we'll end up with a unidirectional link. And that can cause problems in spanning tree because if one of the switches doesn't receive BPDUs because there's a problem with one of the cables, it will transition from the blocking to forwarding state and a loop will be formed. So again, this is a fiber cable. I've got light shining through both here. If there's a problem with one of the cables, so as an example, you connect this to the wrong port on the switch, we'll have a unidirectional link. BPDUs won't be received on this any longer, which means that we could end up with a unidirectional link. Spanning tree will transition to the forwarding state, a loop will be formed, and your network will break. And I'm going to demonstrate that in this video using 3 Cisco switches where a loop is formed and huge utilization of the traffic takes place. These are gig links, and I left it for a while, and I had 700 megabits per second being used on links in a simple topology like this because of a broadcast storm. Okay, so with a fiber cable, once again, we've got a transmit and receive side. If there's a problem on one of these, we'll end up with a unidirectional link and a loop could be formed in spanning tree. As you can see with these SE connectors, you could connect the transmit perhaps on one port of the switch and the receive on a different port of the switch, and therefore end up with a loop because transmit is working, but receive is not working as an example. Or transmit could be broken, and thus BPDUs are not received on the other side. Receive is working, so you receive BPDUs, but BPDUs are not transmitted. So again, end up with a loop. So as I demonstrated with this cable, you could end up with a loop. Okay, so here's our network topology. I've got a 9200 series switch. This switch has a priority of 4096 in spanning tree. In other words, it's going to be the root switch. I've got a Cisco 1000 series switch. This has a priority of 8192. So this will be the backup route. And then I've got another Cisco 1000 series switch here, C1002. This has a spanning tree priority of 16384. So what should happen is hellos from the root bridge or root switch should be sent to the first switch and to the second switch as shown over here. So again, hellos from the root are sent to both these switches. Hellos should be sent from the first 1000 series switch to the second switch. But if there's a problem here because of a unidirectional link, those BPDUs are not going to be received on this alternate port, and that port will transition to become a designated port. So what will happen is this port will become a designated port and start forwarding. And what we'll end up with here is a loop in the topology because this port is now forwarding. So we've got a forwarding port, and a forwarding port. So our network has a loop in it, and this can result in a broadcast storm, which results in the network dying basically or melting because of the amount of traffic sent. And again, I'll demonstrate this problem in a moment using just these 3 switches. Now, if we enable loop guard on our switches, this port will transition to the loop inconsistent state, preventing a loop. So if no BPDUs are received from switch 1, this port transitions to loop inconsistent, stopping the loop in the topology. Now, there are 2 ways to enable loop guard on a switch. You can either do it globally, so type conft spanning tree, the loop guard default. That will enable loop guard on all fiber ports automatically. You can also enable it on a specific interface by going onto an interface and typing spanning tree guard loop. So in this topology, I've got a fiber cable connecting the first 1000 series switch to the second 1000 series switch. So what should happen on gigabit 109, the fiber cable, if BPDUs are not received by the second 1000 series switch, this port should transition to loop inconsistent and stop the loop in the topology. Now, if you enable loop guard globally on the switch and type show spanning tree summary, you'll see that loop guard default is enabled. Now, if no BPDUs are received, the following takes place. We see a message, spanning tree loop guard blocking port and a specific port number. So the switch is expecting to receive BPDUs. If no BPDUs are received, loop guard blocks the port to stop loops. Show spanning tree will show us that that port, which has a role designated port rather than alternate port. Remember, it transitioned to designated because no BPDUs were received on that port. Didn't think there was a loop. Port, because of loop guard, is blocked, and we see loop inconsistent in the output of the show spanning tree command. Recovery is automatic. If BPDUs are received once again, the port is unblocked. Okay, the theory is okay. Much better to see this practically. So let's demonstrate this. Again, I have got a 9200 series switch in the middle. I've got two 1000 series switches, switch 1 at the top, switch 2 at the bottom. On the second 1000 series switch, on gigabit 109, the fiber interface, we're going to enable loop guard and see if it actually works. Now, to simulate this, on the fiber interface, on the first 1000 series switch, I'm going to enable BPDU filtering. Basically, we're going to filter BPDUs, so BPDUs are not sent through this fiber cable, making this port transition to a forwarding state. It'll become the designated port and forward traffic because no BPDUs are received on the fiber interface. And the net result will be that the network melts. Notice here we're seeing 700 megabits per second for the last 5 minutes on gigabit 101 on switch 2. Okay, that's enough talking. Let's put this to the test. This is our topology, our 3 switches on the 9200 series switch. Enable, show spanning tree. This switch is the root bridge or root switch. All ports are forwarding. All ports are designated ports. On the first 1000 series switch, show spanning tree. You can see that its root port to get to the root switch is gigabit 101, which is correct in this topology. Gigabit 109 should be a designated port, which it is. We also have another port which is connected to a PC in this topology. But the important ports are root port and designated port. This is the fiber interface on the switch. Okay, second 1000 series switch. Fiber interface once again, gigabit 109. Show spanning tree. At the moment, gigabit 101 is the root port on the switch, which makes sense. That's the interface to the 9200, which is the root bridge. 109 is an alternate port. As you can see over here, current status is blocking, which makes sense because this is the alternate port to get to the root bridge. Has a higher path cost. Okay, so everything looks good. Show interface, gigabit 101. You can see 5-minute input rate is 0 bits per second. 5-minute output rate is 0 bits per second. Very little is happening on this network. Notice only 6,000 packets in, so many bytes. What about the gigabit interface? Only 5,787 packets. Again, the 5-minute interval is 0 bits per second. So very quiet network at the moment. Okay, but now let's break it. Interface gigabit 109. This is the fiber interface. Spanning tree, BPDU. Filter, enable. Don't do this in a production network, please, unless you're sure about this command, because notice what's going to happen. So I'm going to enable BPDU filtering on the second 1000 series switch. Notice the port is now a designated port. So the status has changed. Notice it's gone to the learning status. Previously, it was an alternate port, but notice now it's become a designated port and it's forwarding. We have now got a loop in this topology, because no switches are blocking ports. The second 1000 series switch, all ports are forwarding. On the 9200 series switch, we see a MAC flap issue. Show spanning tree. All ports are forwarding. On the first 1000 series switch, we're seeing a MAC flapping issue. Show spanning tree. All ports are forwarding. Every port is forwarding in this topology. And that is a problem in spanning tree because we have a loop now. And I'm not sure if you can hear that, but the fan on one of the PCs has now started going. If I look at the task manager on this computer, CPU is increasing a little bit. Task manager here at 21%. But let's send a broadcast into the network. So from this PC, I'll send some traffic into the network. So I'm basically sending a broadcast out into the network. One of the devices is responding. On the switch, we're seeing MAC flap issues. Show spanning tree again, all ports are forwarding. Show interface gigabit 101. What you'll notice now is we are now sending 300 megabits per second of traffic. Notice packets input. Notice the bytes. Notice how many broadcasts and multicasts have been received in the topology. So in this little network, we went from a 0 5-minute input rate to 350 megabits per second. We're now approaching 400 megabits per second. I'll send a few more pings, so a bit more traffic into the network. But what you'll notice is there's a huge increase in the pings now. Notice this is like 2 seconds, whereas before it was 200 milliseconds. Let's have a look at the 9200. So show interface gigabit 101. You can see this interface is now running at 477 megabits per second over the last 5 minutes. Output 467 megabits per second. Look at the number of packets increasing dramatically. So very simple topology. We've now hit 500 megabits per second in a topology like this. The lights are going crazy. I'm not sure if you can see that clearly, but we're getting a lot of flashing lights on the switches because a huge amount of traffic is being sent in this topology because we've introduced a loop. We're now at 528 megabits per second. Send a few more pings. But remember now, this is looping round in the topology. On the Mac at the top there, ifconfig grep 192. This device has an IP address of 192.168.1.2. What I'll do is try and ping one of the other devices in the network, let's say 1.3. We're not getting any responses. Can it ping the Mac? Pings seem to be failing there. On my Mac, things are not going great. I'll try and ping the Windows computer. As you can see, pings are kind of working, but timing out. So definite problems in the network, just trying to ping between devices. On my switches, things are not looking great. Let's look at the utilization. You can see it's now at 660 megabits per second with MAC addresses flapping in the topology. Okay, so let's go to the second 1000 series switch. Show spanning tree, all ports are forwarding. Show interface gigabit 109. This is a 1000 megabits per second interface. It's the fiber interface. Notice output rate 677 megabits per second over the last 5 minutes on a simple topology like this. And you can see packets input is increasing dramatically, 688 megabits per second in a simple topology like this. Okay, so I think I've proven the point. Notice 700 megabits per second over the last 5 minutes. Small topology, only a few devices, 3 switches, network is broken basically because of a broadcast storm. So hopefully this proves the point. Be very careful enabling BPDU filtering in a spanning tree topology. Let's see if LoopGuard can solve this problem. Now, one more thing to show you on one of the switches. Let's have a look at the CPU. So show processors CPU history. As you can see there, 90% utilization of the CPU on the switch. Let's just have a look at CPU without a history. You can see there 87% in the last 5 seconds, 86% in the last 5 minutes. This is not great. Okay, so show run interface gigabit 109. We want to disable this command because we want BPDU sent in the topology so that spanning tree sorts itself out. So spanning tree, BPDU, filter, disable. Show spanning tree, ports are forwarding. Let's have a look at the CPU. CPU is dropping a bit. Back on the second 1000 series switch, show spanning tree. Notice now gigabit 109 is an alternate port. It's now blocking. Show processors CPU on this switch. CPU has gone way down. It was 67% in the last 5 minutes. Last 1 minute, 39%. Last 5 seconds, 6%. On the 9200 series switch, so show processors CPU. Notice 5 minute 27%, 1 minute 8%, now it's 0%, so that's looking a lot better. On the first 1000 series switch, notice CPU is way lower. So history looks good. 6% over the last 5 seconds, it was at 15% and then 52% over the last 5 minutes. So that's looking a lot better. So we've stopped the loop in the topology, but now we want to enable BPDU guard to make sure that if something like this happens again, the port is error disabled. Okay, so now on the second 1000 series switch, let's enable loop guard, conft spanning tree, loop guard default to enable it on all ports. So show spanning tree summary. You can see that loop guard is enabled. Show spanning tree interface gigabit 109. You can see that at the moment the port is an alternate port and it's blocking. If we look at detail on that port, you can see that loop guard is enabled by default on the port. On the first 1000 series switch in our topology, let's enable BPDU filtering on this port once again. So interface gigabit 109, spanning tree BPDU filter enable. So show spanning tree. All ports are forwarding. Notice what happens on the second 1000 series switch. Loop guard blocking port gigabit 109 on VLAN 1. So show spanning tree. Gigabit 109 is a designated port, but it's blocking. Loop inconsistent. If we look at detail on that port, we can see that port 9 is broken, loop inconsistent. The port has transitioned to the loop inconsistent state, preventing the loop in the topology. Show spanning tree again, port is blocking. Show interface gigabit 109. So as you can see, the 5-minute interval is being reduced. Show processor CPU. The CPU is low compared to what it was before. There is no loop in this topology. Loop guard has worked as expected. Once again, show spanning tree. This port is a designated port. It's blocking, loop inconsistent. Okay, but what happens if BPDUs are received? So on the first 1000 series switch again, let's disable BPDU filtering. And notice on the second switch, loop guard unblocking port. Because a BPDU was received, the port now has a role of alternate. Port status is blocking. It's a point-to-point link. Things are working as they should. If BPDUs are received, the port is an alternate port. It's blocking. If BPDUs are not received on that port, then the port moves to the loop inconsistent state, stopping loops in the topology. Hope you enjoyed this video. Please let me know what you think. I'm hoping that these practical demonstrations make it more real world, even though it's quite a lot of effort to set this up and can make things a little bit more complicated, but it's real world, showing you what actually happens with physical equipment rather than a virtualized environment. I'm David Bombal, and I want to wish you all the very best.